It's great to be together once again. I hope everything is well with you. The comet 2P/Encke, or simply Encke, was first observed on January 17, 1786, by the French astronomer Pierre Méchain. Though it may not be as famous as Halley's comet, Encke currently holds the record for the comet with the shortest orbit around the Sun, taking approximately 3.3 years to complete each circuit. In this video, we'll explore why some astronomers are becoming increasingly concerned about its future approaches to Earth, especially from 2027 onward, when it may pass a bit closer to our planet. Could it pose any risks to humanity? Could a collision be possible? One thing is certain. Some in the scientific community are losing sleep over it. There's evidence suggesting that a comet was involved in significant ancient events on Earth, like the abrupt cooling period known as the Younger Dryas, which led to a brief ice age roughly 12,900 years ago. To some scientists, a repeat of such an event can't be ruled out. When it was first discovered, Encke was completing increasingly close orbits around the Sun, so close that it was even nearer to the Sun than Mercury. However, due to weather conditions, Méchain couldn't finalize his observations. The sequence was documented by another French astronomer, Charles Messier, just 2 days later. Nearly a decade after that, on December 7, 1795, English astronomer Caroline Herschel observed and documented it. In the following years, other astronomers like Jean-Louis Pons and Jacques-Joseph Thoulis paid close attention to the comet. In 1818, Pons proposed that Encke might be a periodic comet, meaning it orbits the Sun in a short, consistent cycle. The following year, German astronomer Johann Franz Encke, then director of the Berlin Observatory, attempted to calculate the comet's orbit and determined that it had a period of only about 3.5 years, aligning with previous suggestions. Based on his calculations, Encke predicted the comet would return in 1822. Indeed, in June of that year, Karl Rümker, a German astronomer in Sydney, Australia, observed the same comet, which has since been known as Encke. While comets are typically named after their discoverers or the observatory or telescope used in their discovery, Encke was named after Johann Franz Encke because he was the one who successfully calculated its orbit. Still, some credit might also go to Jean-Louis Pons, who first suggested its periodic nature, or to Méchain. The P in 2P/Encke indicates it is a periodic comet, meaning it has an orbital period of less than 200 years. Like Halley's comet, designated 1P/Halley, which has a much longer period of around 76 years, Encke has been regularly observed by the astronomical community since Johann Encke's prediction. Encke is also associated with the Taurid meteor shower, caused by debris left in its path. Known as the parent comet of the Taurids, these meteor showers appear annually around October and November, often featuring bright fireballs. Meteors traveling at incredibly high speeds of over 100,000 kilometers per hour. These fireballs can sometimes be as bright or even brighter than Venus, with a visual magnitude around -4. For reference, the lower the visual magnitude, the brighter the object. For example, the Moon has a magnitude of -12.6, and the Sun has -26.7. Unlike many long-period comets, Encke is relatively small, with a nucleus of around 4.8 kilometers in diameter. Each pass by the Sun causes it to release gas and dust, though it is less active than many other comets. In 2007, NASA's Messenger probe, en route to Mercury, observed Encke during one of its close passes to the Sun, providing valuable data on its composition and behavior. Over the years, due to gravitational interactions with planets, especially Jupiter, Encke's orbit has shifted slightly, but its short and predictable orbit allows frequent observations compared to many other comets. After countless orbits near the Sun, much of Encke's ice has likely evaporated, resulting in a relatively short tail. As we know, comets are small celestial bodies made of ice, gases, and dust that orbit the Sun. Each comet has unique characteristics, and they are also categorized based on their tails, which can be composed of either ions or cosmic dust. The ion or gas tail forms as the comet approaches the Sun, where heat causes the frozen gases in its nucleus to sublimate, releasing volatile molecules like water vapor, carbon dioxide, ammonia, and methane. These molecules are ionized by the Sun's ultraviolet radiation, losing electrons and becoming electrically charged. The solar wind, a steady stream of charged particles from the Sun, pushes these ions away from the comet, creating a tail that always points directly away from the sun, regardless of the comet's direction of travel. This ion tail is typically straight and has a blue hue due to the fluorescence of the ionized molecules. In addition to gases, the comet's nucleus releases dust particles as the frozen material sublimate. These small particles reflect sunlight, forming a bright, visible dust tail. Influenced by the pressure of sunlight, this tail is pushed away from the nucleus, but tends to be curved rather than straight, as dust particles are heavier than ions. The dust tail follows the comet's orbit, creating an arc that can stretch for millions of kilometers and generally appears yellowish as it reflects sunlight. Depending on the comet's activity level and its distance from the sun, both types of tails can extend millions of kilometers into space. As the comet moves away from the sun, it cools, sublimation slows, and the tails gradually disappear until the comet's next close approach. Comets traveling within our solar system are believed to originate from two distinct regions, the Kuiper Belt and the Oort cloud. According to various studies by astronomers worldwide, short-period comets are usually thought to come from the Kuiper Belt, a region of the solar system beyond Neptune with a vast number of icy objects and primordial bodies left over from the solar system's formation. This belt is one of the primary sources of short-period comets like Encke. Kuiper Belt objects are composed mainly of ice, rocks, and other volatile materials, which makes them susceptible to gravitational disturbances that could eventually propel them toward the inner solar system. Encke is believed to have been originally a Kuiper Belt object, which, through gravitational interactions with giant planets like Jupiter, was directed into a closer orbit around the Sun. There is also an intriguing hypothesis regarding Encke. Have you ever heard of the Tunguska event in Siberia in 1908? On June 30th of that year, a massive explosion occurred in a remote Siberian area, flattening approximately 2,000 square kilometers of forest. Some scientists believe the event was caused by a celestial object, possibly an asteroid or a comet, which exploded in the atmosphere before hitting the Earth's surface, releasing an estimated 10 to 15 megatons of energy, about 1,000 times more powerful than the atomic bomb dropped on Hiroshima. Given that Encke is linked to the Taurid meteor shower, some astronomers suggest the Tunguska object might have been a larger fragment or piece of material related to Encke, as it sheds debris along its orbit. Earth crosses the Taurid meteor stream twice a year, and this stream contains fragments of various sizes. Some particles are small and manifest as meteorites, but the stream may also contain larger fragments, possibly like the one thought to have caused the Tunguska event. If Encke was indeed behind events like the Younger Dryas cooling and Tunguska, it's possible that it could lead to another major event or even trigger climate changes. According to some scientists, Encke might not only influence climate but could also cause a global catastrophe. The Younger Dryas period is one of the model scientists used to predict potential impacts on humanity starting in 2027 when Encke will return. So, stay tuned to understand more. Around 12,900 years ago, Earth experienced a sudden freeze that lasted approximately 1,300 years. Scientists suggest this intense cooling may have been triggered by the explosion of a large comet. How so? Two recent studies published in the Journal of Geology, a renowned U.S. publication on geology since 1893, reveal ice and sediment samples supporting a climate shift caused by an impact event, known as the Younger Dryas. Analysis of samples from various locations around the world, formed during the time of impact, suggests that massive wildfires created a sun-blocking cloud, leading to an ice age lasting just over 1,000 years. The theory posits that a fragmented comet caused this catastrophe, with its pieces impacting Earth. The towering smoke columns from these widespread fires would have risen into the atmosphere, creating a barrier that blocked sunlight. Without industrial activity or greenhouse effects from human activity, the surface quickly cooled, plunging the world into an ice age that changed the course of human history. But how do we know Encke might be involved? Encke has been within the solar system for thousands of years, showing signs of considerable wear from random impacts over time. Studies suggest that the comet responsible for the Younger Dryas was likely around 100 kilometers in diameter. What remains of it still orbits between the Sun and Earth. Both the shape and size of this comet, as well as its trajectory, have evolved to form the orbit we see today. Although we cannot be completely certain, Many researchers see this as a strong possibility. The Younger Dryas theory also helps explain the mass extinction of large North American mammals, such as saber-toothed tigers, mammoths, giant sloths, and mastodons, about 11,000 years ago. Could this happen again? With today's population levels, the potential consequences are significant. Calculations indicate that if Encke remains unobstructed, it will pass by Earth again in 2027. This annual passage through the Taurid meteor stream brings an increased risk. Imagine if our planet's gravitational pull drew Encke closer, creating an apocalyptic scenario where hundreds of meteoroids might collide with Encke's coma, as in the Younger Dryas. The immediate result would be small explosions, causing fragments of various sizes to break away. Some fragments might follow Encke, but others could be drawn towards Earth by its gravity, falling into our atmosphere. Smaller fragments would typically burn up during entry, while larger pieces, as history shows, could strike the surface. We're not talking about just a few dozen meteors here, but potentially thousands, or even tens of thousands, crashing onto land and sea worldwide. Picture thousands of meteors striking buildings, houses, and dense forests in summer, resulting not only in destruction and crater formation, but also igniting fires globally. The climate impact could be severe, with dense dust and smoke invading the atmosphere, potentially leading to another ice age as it did nearly 13,000 years ago. Is this scenario possible? Well, yes, though the situation is somewhat less dire, thanks to the fact that Encke likely lost much of its mass since then. Today, Encke's nucleus is only about 4.9 kilometers in diameter, far smaller than the estimated 100 kilometers size of its predecessor. So, unless Encke drastically changes course and collides directly with Earth, something we all hope to avoid, it's unlikely to cause massive damage. But there is still much we do not know about the universe and its nature. Let me know your thoughts on this topic, and thanks for watching. See you in the next video.